Alright, silly people, here's the situation. We have a time-independent wave function, psi of x and 0, um, that we are going to normalize and then evolve it in time, and then find expectation values of position and momentum, and also discuss Iron Fist's theorem. So let's get to it. Uh, to normalize this, we just need to take the square modulus of it, uh, which is a little bit more involved than usual because this is a mixed state. So we'll have that it has an overall factor of a squared on the outside of the integral. But then in the integral, we're going to have a term proportional to 9 times the square modulus of psi 0 plus 16 square modulus psi 1 plus 12 psi star 0 psi 1 plus 12 psi star 1 psi 0. And when we take this integral, we'll keep in mind the fact that all of these wave functions are orthogonal to each other. So in general, psi m star psi n will be equal to a Kronecker delta psi mn, which means all of these cross terms, when we do the integral, are actually going to cancel out, and these integrals will just go to 1. So we have a squared 9 plus 16, which is a squared 25, and you set that equal to 1 to normalize it, so you find that a is equal to 1/5. Okay. To evolve the wave function in time, we just need to multiply every position wave function, time-independent wave function, and multiply it by its e to the minus I e n t over h bar. So in our case, we have the normalization factor of 1/5 out front. We have 3 times psi 0, and then e to the minus I e0 t over h bar, plus 4 psi 1 e to the minus I e1 t over h bar. That's it. We can make that prettier by remembering that the energy levels for the harmonic oscillator are h bar omega times n plus a half. So we can write this now in terms of omega as just being 3 psi 0 e to the minus I omega t over 2 plus 4 psi 1 e to the minus I, or 3i omega t over 2, right? And then Griffiths asks us to go ahead and calculate the square modulus of this. It's pretty worth doing. So the 1/5 outside will get squared and go to 1/25. You'll have the terms proportional to 9 times the square modulus of psi 0 plus 16 times the square modulus of psi 1. But then we have those cross terms again. And now that it's time dependent, it's going to get a little weird. So first off, you're going to have 12 times psi 0 star, so we're taking the complex conjugate of the psi 0 stuff, times psi 1, so you'll have e to the minus 3/2 plus 1/2, so minus 1, e to the minus I omega t. That's it. And then another term, 12 psi 1 star psi 0 e to the plus I omega t. And we can take advantage of the fact that all of these wave functions are real, the position wave functions anyway, to combine actually the terms. So 16 psi 1 star, or psi 1 squared, plus 12 psi 1 psi 0, and then we combine them, so it'll be e to the I omega t plus e to the minus I omega t in there. We can simplify this even further by making use of the definition of the cosine function as being e to the iz plus e to the minus iz over 2. And throw that in, and so we get 1 over 25 9 psi 0 squared plus 16 psi 1 squared plus 24 psi 1 psi 0 cosine omega t. So we found that the square modulus oscillates with a frequency equal to the classical frequency for the harmonic oscillator. But Griffiths points out, what if we were looking at psi 2 instead of psi 1? Then if you do all the math, it would give you a cosine 2 omega t instead of cosine omega t, but everything else would be the same. It's just changing the frequency. Then we're asked to find the expectation value of position. The calculation of this isn't going to be all that different from what we just did, because it's just going to be the integral over all space of psi star x psi dx. Write out all the terms before I do anything with it. So for us, it's looking like 1/25. Then we have the integral from minus infinity to infinity of 3 psi 0 star e to the I omega t over 2 plus 4 psi 1 star e to the 3 I omega t over 2 times x times the wave function from before. So minus I omega t over 2 plus 4 psi 1 e to the minus 3 I omega t over 2 dx. And then when we combine everything, I'm actually gonna split this up into a bunch of integrals. We'll have 9 times the integral psi 0 star x psi 0 dx plus 16 psi 1 star x psi 1 dx plus a couple of cross terms which are pretty different from each other. Will just be 12 psi 0 star x psi 1 e to the minus I omega t, right? Yes. And then dx plus 12, I'm running out of room, psi 1 star x psi 0 e to the minus 3 I omega t over 2 from minus infinity to infinity. And I think I proved in the last problem from Griffiths on this channel that in general the expectation value of position for any one particular eigenstate of the harmonic oscillator goes to 0. So we can handily cancel those out. and then we're just going to be left with 12 over 25 times, it'll be the integral psi 0 star x psi 1 dx e to the minus I omega t plus integral psi 1 star x psi 0 dx e to the I omega t. Now we can make use of an identity specific to the harmonic oscillator. We can change the position operator into h bar over 2m omega times the sum of the raising and lowering operators. So that's going to look like raising and lowering, so but also with the radical out front of everything, 2m omega. We're going to have psi 0 star a plus plus a minus psi 1 dx e to the minus I omega t plus integral psi 1 star a plus plus a minus psi 0 dx e to the I omega t. Okay, so applying the raising and lowering operators, then you're going to have a root 2 integral psi 0 star psi 2 dx plus, and all of this is going to be multiplied by the exponential at the end, so plus just root 1, so 1 times the integral psi 0 star psi 0 dx times e to the minus I omega t plus also in parentheses the integral psi 1 star times psi 1 dx times 0, because the lowering operator acting on psi 0 gives you 0, and that is times e to the I omega t. And also this integral here is going to go to 0 because it's the orthogonality condition again. So we just have 12 over 25 root h bar over 2m omega times e to the I omega t plus e to the minus I omega t. And again, we can use the definition of the cosine function to turn this into a cosine. And that is pretty nifty. Similarly, the expectation value for momentum can be calculated. That is psi star p psi dx. Skipping ahead to the bit where I am just doing the cross terms, that's looking like 12 over 25 times psi 0, the integral of psi 0 star p psi 1 dx e to the minus I omega t plus integral psi 1 star p psi 0 dx e to the plus I omega t from minus infinity to infinity. So what makes this different is the you can change the momentum operator into a different thing, which is just I times the square root of h bar m omega over 2 times now the difference between the raising and lowering operators. So with that in mind, we'll have 12 over 25 times I root h bar m omega over 2, and then expanding the operators in here, we'll have a plus minus a minus psi 1 dx e to the minus I omega t plus integral psi 1 star a plus minus a minus psi 0 dx e to the I omega t minus infinity to infinity. I'm going to go ahead and switch the sign on this because I know where we're going to end up. Minus 12 over 25 I h bar m omega over 2 times, we'll have an integral with just root 2 integral psi 0 star psi 2 dx minus the integral psi 0 star psi 1, no, it's psi 0 again, dx, all times e to the minus I omega t, and also plus, again, we only have the integral psi 1 star psi 1 dx e to the plus I omega t, all from minus infinity to infinity. So this time we have, factoring out an additional factor of 2, we just have e to the I omega t minus e to the minus I omega t all over 2I. And that is actually the definition of the sine function. So sine z equals e to the I z minus e to the minus I z over 2I. So doing that, we have minus 24 over 25 square root h bar m omega over 2 times sine omega t. If you look back at the expectation value that I got for x, it was proportional to cosine omega t, and then this one is proportional to minus sine omega t, and you can check this yourself. I would have gotten the same thing if I had just taken the mass times the time derivative of the expectation value of x, because that's how Ehrenfest's theorem works. It also asks us to check Ehrenfest's theorem in this iteration, that the time derivative of the momentum will be equal to minus the partial derivative of x of the potential. Well, we can go ahead and take the time derivative of our expectation value of p to be just minus 24 omega over 25 times square root h bar m omega over 2. But on the right-hand side, we're going to have to, first of all, define the potential for the simple harmonic oscillator, that being that V equals m omega squared x squared over 2, so that we know we're just taking the expectation value of minus m omega squared x. Um, and we can go ahead and pull out the m and omega squared from here uh, because those values are constant, and we just have the expectation value of x, which for that we got 24 over 25 square root h bar over 2m omega cosine omega t. And I'm now realizing that I totally forgot to write cosine omega t up here when I was taking the very clever um, time derivative. But yeah, you can already probably see how these are going to be the same, but I'll go ahead and make sure, because I'm going to factor through a factor of m and a factor of omega to the radical to have h bar m squared omega squared over 2m omega, just 2m omega. Yeah. Cosine omega t, and then now this is looking like, canceling stuff out in there, just h bar m omega over 2 times cosine omega t. And yeah, they match up pretty nicely, so we're all good there. The question also asks us what energies we can actually observe for this wave function. Um, and just because it's a mixed state with time dependence doesn't mean that we're not just going to find that if we observe it, we get either E1 or E0 with probabilities C0 squared and C1 squared, which in our case ended up being like 9/25 and 16/25, which do add up to 1, so it's perfectly sound probability theory there. And so yeah, that's what you're going to observe if you look at this. All right.